Swayam Prabha. Digital India. Educated India.
Okay, so good morning everyone. So today what we are going to do is we are going to look at communication complexity and how we can use communication complexity to give depth lower bound to circuits computing various problems. Okay, so in particular what we will do is we will look at a very famous theorem due to Karchmer and Wigderson, who gave a tight connection between the communication complexity of protocol and the corresponding the depth lower bound of a corresponding circuit computing it. Okay, so we'll come to that. So first let's lay the groundwork for communication complexity. Let's just discuss the notations and the definitions. So okay, the communication problem corresponding to A or to the relation R, let's say it's a relation X cross Y cross Z. So suppose we have a relation over three sets X, Y and Z, X cross Y cross Z. So the corresponding communication problem is defined as follows. So Alice is given small x belonging to capital X and Bob is given y belong to capital Y and they need to output Z in capital Z such that X, Y, Z belongs to R, or report that no such Z exists. Okay, so we have two parties. We have Alice and we have Bob. So Alice has X, Bob has Y. Okay, and now they need to communicate. Okay, so they need to figure out. So of course Alice doesn't know what Y is and Bob doesn't know what X is. So they need to communicate bits among themselves and figure out a Z such that XYZ belongs to R, if such a Z exists. And if Z doesn't exist, they need to say such a Z doesn't exist. Now, how does the, yeah, so as I said, okay, so specific example is if suppose that Z equal to GXY, then Alice and Bob computes the function G. Okay, so as I said, so they send bits to each other during the execution of the protocol, to be more precise. The in a given round, the bit sent depends on the input of the corresponding player and the bits communicated in earlier rounds. Okay, so basically, so in the first round, let's say one of the two parties, let's say we start with Alice. So Alice sends a bit. So because it's the first round, so Alice's bit would only depend on the input of the corresponding player, that is Alice's input X. Now Bob will have the bit that he receives from Alice. Okay, so Bob will have his own input, that is Y, along with the bit that he receives from Alice. So the bit that Bob sends would depend on both these two. And then in the second round, the bit that is sent by Alice would depend on her input, which is X, and the bit that were transmitted in the earlier round. So this is how the communication proceeds. Okay. And okay, so now we define what is the communication complexity. So the communication complexity of a protocol pi for an or on an input x comma y, okay, we'll write that as C pi x comma y is equal to the total number of bits communicated to execute pi on the input xy. Okay, so for a given input xy, if Alice has x and Bob has y, what is the total number of bits that is communicated to generate the output is C pi xy. The communication complexity of a protocol pi, okay, so we define C of pi as the maximum communication complexity over all pairs of inputs. Okay, this is the standard way. And the communication complexity of a relation, okay, so suppose we have a relation R. So for a relation R, communication complexity of R is defined as the minimum over all protocols of C of pi such that pi computes R. Okay. So now we know what we mean by the communication complexity of a relation. So we will look at two types of relation, and in fact both are sort of similar. So we consider two types of relation. The first one is, so suppose we have sets A and B consisting of strings, consisting of n-bit strings such that A and B are disjoint. Okay. Now we define the relation R AB as all, so it tuples x, y, I such that x belongs to A, y belongs to B, and the ith bit of x is not equal to the ith bit of y. Okay. So suppose, so think of two sets. Suppose we have two sets that are disjoint, okay, which means that, well, there has to be some string that is different in both the sets. So we define well, and assume they are non-empty as well. So if they're empty, of course this is not true. Assume both A and B are non-empty. So there has to be some string in both A and B. So we define the relation RAB as follows. Okay, so it is all tuples of this form. So what is RAB? So RAB is basically a subset of X, or not X, so A cross B cross, the set consisting of 1 to n. Okay. The second type of relation that we define is what is more appropriate for us for a function. So let f be a Boolean function. F is a function from 0, 1 to the power n to 0, 1. So we define R of f as equal to R f inverse 0, comma f inverse 1. Okay. So basically, if there is a protocol for R of f, it means that Alice is given a string which evaluates to 0, Bob is given a string which evaluates to 1, and they need to agree on an index on which both x and y differ. Okay. So this is roughly the framework that we would be considering. So let's look at an example. Okay. So consider the XOR function. So what is the XOR function? So you are given input string. So you're given, let's say, an input, and you output 1 if it has an odd number of ones, and 0 if it has a even number of ones. So it's the same as the parity function. So now we will define a protocol. So first of all, we need to define what we mean by the corresponding communication problem here. So we define the communication problem as follows. So in the corresponding communication problem, Alice has X such that X1 parity up to Xn is equal to 0, and Bob has Y such that Y1 up to Yn is equal to 1. Okay, so both Alice and Bob have 2 strings. So one way to, yeah, so because they must be of different, yeah, so this actually does not belong to Zoran and this belongs to Zoran, right? So yeah, so Alice has this, and now they have to find out, they have to communicate among themselves, and they have to find out a bit on which X and Y differ. Okay, so how do they proceed? So the idea is you apply a divide and conquer approach. Okay, so you kind of use the fact that, well, for example, if I have n bits, okay, whose parity is 0, then if I look at the first n by 2 bits, if the parity of the first n by 2 bits is 1, then the parity of the next n by 2 bits also has to be 1, and if the parity of the first n by 2 bits is 0, then the next n by 2 bits is 0. And if I have parity of n bits which is 1, then the opposite is true. So basically, if the first n by 2 bits is 0, then the next n by 2 bits must be 1, and vice versa. So this is the principle on which the protocol is designed. Okay. So here is the protocol. So let's say that we have Alice who has X and Bob has Y. So let's say Alice begins. So if n is strictly greater than 1, compute A1 which is equal to the parity of the first n by 2 bits, and send A1 to Bob. Okay. Now what Bob does is, Bob computes B1 which is equal to A1 parity Y1 up to Y n over 2, and send B1 to Alice. Okay. Now if what is the condition? If B1 equals 1, then what should we do? What does it mean if B1 equals 1? then they should recurs on the first half, right? You can actually check the case. Okay, so let's just look at one case, the other case is similar. So suppose, so case 1 is, suppose let's say that A1 was equal to 1, which means that yeah, exactly, yeah. So if A1 is equal to 1, it means that the parity of the first half of Alice, the parity of first half of X is 1, and if the parity of the first half of X is 1, which means A1 is 1, then the parity of the first half of Bob must be 0, right? So therefore, if they recurs on the first half, then you have two inputs on which they differ. Okay, so then recurs on first half, else recurs on second half. Okay, and you do this, and now when do you stop? So you stop when, and what is the invariant that you are maintaining at each round? So the invariant that you are maintaining at each round is that the current string that you have, their parities differ. So that is the invariant, and of course in each round the size of the string gets halved. So stop the protocol when n is equal to 1. At this point, we, or Alice and Bob, have an index I such that the inputs are different. So basically the index at which they stop. Okay, so the protocol is simple. So what is the communication complexity of this protocol? So suppose let's give this a name. So let's call this as pi XOR. So the communication complexity of pi XOR is how much? How many rounds would there be? There is ceiling of log n rounds, and in each round we communicate 2 bits. So we have a total of 2 log n bits that are communicated maximum. Okay, which means that well, the communication complexity of XOR is at most 2 log n, or let me be a little bit more. So actually I'm not looking at exactly XOR, but the relation corresponding to XOR. Okay, so I haven't defined it formally, but you can define what is the relation corresponding to the XOR function. So this is there because there is a protocol, therefore it is at most 2 log n. Now what does this say? So we are looking at, so far we have been looking at communication complexity, but what does this say about the connection between the communication complexity of XOR and circuit depth? In other words, why are we considering? So we have to kind of, so we have two different models. So we have two different frameworks. So one is I have a function, and the first framework is I have to design a circuit for that function, and I study the size, the depth of the circuit. The other is I have a function and I want to study if I look at communication problem corresponding to this function, what is the minimum number of bits in which that problem can be solved? What is the minimum communication complexity in which that problem can be solved? So these are the two frameworks. So now I want to study what is the connection between these two frameworks. To get to that, I have to define, right? So I have to define the relation, because for communication complexity, the way we have defined it, it is for a relation. So for a function, I have to define a relation. So this is, I mean, this is one way to do it. You can actually, well, any other way is actually the same. So now, what can we say about the, let's say, the minimum depth of a circuit computing XOR? Okay, so we are only looking at, okay, so for the purpose of this topic, we are only looking at bounded fan-in circuits. Okay, so let's say we are looking at circuits over AND or and NOT gates. Okay, so the question is, okay, let me also define one more term here. I think I have defined it earlier, but probably not. So let me do it. So for a Boolean function f, how do I write this? Let d of f denote the minimum depth of a circuit computing f over AND or and NOT gate. So we assume these are gates whose fan-in is bounded by 2. Okay, so d of f is the minimum depth circuit that computes f. So what can we say about d of XOR?